For more information, please visit SGMAK Associates website.
In this module, I'm going to discuss two problems where we're making decision based on net present value of all future costs. So first example captures infinite planning horizon. So let's look at the two alternatives that we have. So alternative A has an initial cost of $500,000, annual cost of $35,000, and you have a recurring cost, annual recurring cost of $350,000 every 15 years, and that project is supposed to have infinite life. You can think about resurfacing a road with an initial stretch of a road with initial cost. You've got an annual operating cost and then a recurring repair cost every 15 years. And alternative B uses a different method, different materials, has a little initial higher cost, a lower annual cost, and but a little higher annual additional recurring cost every 15 years. Objective is to select the best alternative when you have a desired minimum attractive rate of return of 12%. So the thing to keep in mind in this case, we are dealing with two alternatives, both have infinite life. So we'll compare it based on net present value of all future costs. For alternative A, net present value of all future cost is the initial cost right now. That's what we have done. Since it's like a capitalized cost, we have converted all future cost into a equivalent uniform annual cost first. And that is given by this expression within the brackets, 35,000, which is annual operating cost, plus 350,000 multiplied by the factor A over F at 12% rate every 15 years, converts into equivalent annual cost. When these two are added together, then you divide by the desired rate of return, that gives you the net present value of a single cost at time 0. So together they give you a total cost of $957,000 and $957,916. So key thing to note here is how the annual cost and a recurring cost every 15 years converted into a single sum at time t equals 0 right now at present. Following the same reasoning for alternative B, we have initial cost of $700,000 plus first you calculate the equivalent uniform annual cost, which is given by 25,000 plus 450,000 multiplied by the factor, converting feature to an annuity, A over F 12 and 15. Then the total annual cost divided by the interest rate to get the present value. And when you add it to the initial cost, it gives you a $1,122,000.83 as total cost. So of course we are dealing with just the cost aspect of it, assuming the benefits are the same. So in this case, based on the data given, we'll select the alternative that has a lower cost, lower net present value of all future costs. So based on that reasoning, alternative A is the preferred alternative. Moving on, there's another example where some of you are, all of us familiar with this credit card payment, how you repay your credit card payments. Here's the problem statement. The current balance in your credit account is $8,574. You're paying an interest rate of 18% APR compounded monthly. You're required to make a monthly payment of $225. How long will it take you to repay the loan? You're paying an interest rate of 1.5% per month. You got an initial balance of $8,574 and you're paying $225 per month. So if you solve this equation, 8574 equals 225 multiplied by the factor that converts annuity to present value, P over A, 1.5%, unknown period N. Solving that, we get N equal 57. So it takes 57 months, close to 5 years, for repayment at the current payment plan. Now, as a general rule for comparing two alternatives, when we're comparing two alternatives, we have the following two variations. Alternatives have equal service lives. Then we make decision based on the net present value of the alternatives. If you have unequal service life, then you have two choices. Either you use a common time frame during which each alternative is replaced multiple times, or is solved based on an equivalent annual benefit minus equivalent annual cost basis. We give a pictorial representation next. If you have equal service life comparing two alternatives, use net present value. If you have unequal service life, we got two choices. Use a common time frame. This approach makes the problem a little longer, computation a little bit tedious. A better approach is based on analysis based on equivalent uniform annual benefit minus equivalent uniform annual cost. So let's run through an example. We're comparing two alternatives A and B. The cost elements are given. A has initial cost of $300 and uniform annual benefit is of $1,800, useful life 4 years. B has the initial cost of $10,700, uniform annual benefit of $2,100, and useful life of 8 years. We need a desired MARR of 10%. So in this case, since alternatives have unequal life, one approach is we use a common time period of 8 years, during which B runs through one life cycle, and A runs through two life cycles. So after 4 years, we replace A with an identical unit that runs for another 4 years. So here's the cash flow diagram looks like. For A, we have replaced after 4 years with the identical cost structure. B just goes through one cycle of 8 years. So net present value of B is $503.5, and net present value of A, the cash flow diagram converting into net present value. So we have a net present value of $683. Since A has a higher net present value, A is preferred. Now, other approach, if we solve based on equivalent uniform annual benefit minus equivalent uniform annual cost, then we don't need to correct for unequal service lives. Idea is that at the end of useful life, the equipment is replaced with the identical unit that has the same cost structure. So for alternative A, Uniform annual benefit minus uniform annual cost comes out to be $327.85. And for alternative B, just following a cash flow diagram, all you're converting the initial cost into uniform annual cost, and that comes out to be $94.82. So again, you can look at this number as a net profit on an annual basis. Since A offers a higher number, A is better alternative compared to B. So both approaches give you the same solution, but alternative B is preferred. As you can see, computationally less tedious because you don't have to correct for unequal service lives. Alright, so hopefully you'll find these two examples useful, and we'll have more discussion with some more example problems later. Okay, bye.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.